Okay, so today we're starting chapter 7, which is all about integration. I think we're just going to do 7.1, 2, and 3 and skip 7.4 and 5 because those are the key things that you guys are going to need for next year. To start with 7.1, we're actually only going to do the first bit of it, so we're not going to do Euler's method. But we are going to do slope fields, and we're going to start by talking a little bit about the integrals and how we go about them and some of the rules, because we did some stuff about integrals last chapter. So in chapter 6 we figured out, okay, the integral is the area under a curve, and the integral is the opposite of a derivative, right? So if we think through what did we have to do to get the derivative, we work backwards to do an integral. We also talked about the fundamental theorem of calculus and how that relates to an integral. So we're going to kind of tie that in and tie that together first. So the first thing that I want to look at is actually our identity sheet. So on this we have a bunch of derivatives, right? So this is the first page. We have a bunch of derivatives. So it tells us that the derivative of sine x is cos x, okay? Now, if we think about this backwards, on the next page is a list of integrals. Okay, so there's some of the rules that we've actually been using. So if we're doing the integral of one function plus another function, we can split it into separate. If we have an integral of a constant times a function, that constant can come out, and then we can do the integral of that function. This is actually something that we've been doing a ton without actually having ever explicitly explained the rule. So if I have the integral of, let's say, x cubed, if we wanted to figure out what that is, we'd say, okay, if we thought about it as an antiderivative, we know that it must have started as an x to the 4. And then we would say, okay, if this turned into that, it must have had a 1/4, so that when the 4 dropped down, it would multiply with that 1/4, and then this would turn into a 3. So notice how this fits this rule. So the integral of x to the n, in this case we chose n equals 3, is x to the n plus 1, so 4, divided by n plus 1. There's the 4 as well. So this is the rule that we've been using without knowing that we were using it, okay? And then there's a whole bunch of different integrals on here as well. What I want to point out is the relationship between the derivatives and the integrals. So if we look at the derivative of sine x is cos x, notice how when we look at the integral of cos x, we get back to sine x. So there's that opposite relationship. If we look at the derivative of cos x, it's sine x. If we look at the integral, we get negative cos x, right? So see those relationships. The other thing, and we kind of skipped over some of these in chapter 6, if I asked for the integral of secant squared x, it's like, oh my gosh, how do we deal with the squared and blah, blah, blah. This is where this formula sheet plus the knowledge that a derivative is the opposite of an integral is super helpful. So see how the derivative of tan x is secant squared x? That means the integral of secant squared x dx is tan x plus that constant. Remember that c value is just, so maybe the graph looks like that. That c value tells you whether or not it's shifted up and down, okay? And we'll look at some examples of when that c value needs to be specified in a second, okay? So basically there's integrals for all of these different functions. So see how we had those inverse trig derivatives. And so the derivative of tan inverse x is 1 over 1 plus x squared. So the integral of 1 plus 1 over 1 plus 1 plus x squared, it's in a different order, but same thing, is tan inverse, okay? If we see the integral of e to the x, that just is e to the x, because remember how the derivative of e to the x just was e to the x. We see the derivative, the integral of 1 over, so this could also be written as 1 over x times dx, is ln x. because we saw that the derivative of ln x was 1 over x. So it's basically your relationship that goes back and forth, and it's all listed here for us. There's also this table of antiderivatives. Antiderivatives is one way to calculate an integral, so you can use this as well. So if you have a function of 0, the antiderivative is 1, right? If you have a function of 1, the antiderivative is x, because if you have, if you're doing the derivative of x, that's going to give you a 1, right? So the opposite way is your integral. So derivative, integral. If you have a function of 1 over x, the antiderivative is ln x. If you have e to the kx, so not just e to the x this time, it's going to be 1 over k times e to the kx, because remember how the chain rule works. If you've got e to the 2x, and that's the derivative, to get back to the original, it would have been e to the 2x. That would stay the same, but then you would have multiplied by, when you did the derivative, you would have multiplied by 1/2, or by the 2, the derivative of this guy, so that would have canceled with that 1/2. So this is your original. Same with sine and cos if you've got constants in there, so chain rule. Okay, we'll talk more about this as we go, but just so you guys know that this is here, this is a resource to you, so I'm going to reference that more now that we've kind of talked about it. So if we have problems with all of this in here, so the first thing that we're going to do is find all of the functions for y that satisfy the derivative of y with respect to x is this, okay? If it's all of the functions, this could be any c value, right? Because it's any shift up and down that gives this as the slope, right? If I draw this graph and this graph, let's try and make it a little bit more accurate. The slope along every single x point is the same. It's just been moved up and down. So that's what that c value is doing, right? Because this is telling you your slope is consistent. The original function might have just been shifted up and down a little bit. So if we want to find all the functions for y, basically what we're doing is we're finding an antiderivative or an integral of this function, okay? So it's going to be y is equal to, if this is the derivative, we have to think about what it started at, okay? So we can look at our integrals table. So the integral of sine x is negative cos x, which makes sense because if we did the derivative of this, the derivative of cos x is negative sine x, and then the negatives would cancel each other out, okay? Then we need to do the antiderivative or the integral of e to the negative x. So I'm going to look at, let's look at this one. So notice how in this case that a value is a -1, right? It's e to the -1x. Okay, so what that means is the integral, so it's going to be minus, that -1 needs to come down in front, so 1 over 1 to the or 1 divided by -1, and then e to the -x. Okay, so notice how this is all just going to simplify. And then this guy, we're saying, okay, 8, and then what's the integral of this guy? So this must have started as x to the 4, and then that 4 would have had to drop down. So when we simplify this, this is going to be negative cos x. This is going to turn into a plus e to the -x. 8 divided by 4 is 2x to the 4. And then because this is any function, we need to add that plus c. So there's that like any coming into play. It's like right on the edge of the video, sorry. Okay, so if we want to find all the functions that satisfy y for this one, again, we're doing the antiderivative. We have to think about, okay, if my function looks like this. My antiderivative is ln x. So this 1 over x, this would have started as ln x. Okay, this one we've got 4 divided by 1 minus x squared, all square rooted. So see how that looks a lot like this guy, okay? Something divided by 1 minus x squared, all square rooted. So this is just going to be minus 4 of the sine inverse of x, because remember this whole thing could be written as minus 4 times 1 over 1 minus x squared. Okay, and then that plus c adds all of the options. Find all the functions for y that satisfies the derivative is this guy. Okay, so if we're having the derivative is a secant squared of something, then we're looking at the integral of a secant squared. It must have started as tan. So y would be tan of x to the 4. Okay, where did this come from? Okay, when we do the derivative of this, if we work backwards, this is going to be secant squared of x to the 4 multiplied by 4x cubed because of that chain rule. So we don't have to do a separate step, we just have to think through the chain rule, right? Because we'd have to do the derivative of what's inside here. And then that any function means that we have to add a c value, okay? Then the other way that we can approach this is we can solve initial value problems. So this one, there won't be like a c value, there will be an actual constant, how much it moved up or down. So the first thing that we have to do is figure out what our y function is. So if this is the derivative, what's the original? So y would equal, so we're going to look at our formula sheet. We have a 1 over 1 plus x squared, nothing square rooted, so that's going to look like this guy. So this must have been tan inverse of x, okay? Then we've got a 2x ln 2. So for this one, where is this one? Where's something x? Okay, here it is. So we've got 2 to the x. The x is in the variable, so a in this case is 2. Okay, so the antiderivative of that guy, the integral of this guy, would be of just the 2 to the x would be, according to our formula sheet, 2 to the x divided by ln 2. Now this is just a constant, so it's still going to get multiplied, and then that's actually going to cancel out. Okay, so we've got y is equal to tan inverse of x plus 2 to the x, and then we would have to add that plus c. Okay, then it's going to tell us that y is equal to 3 and x is equal to 0, and we're going to plug those things in to figure out what the c value is. So we're going to go y is equal to 3, tan inverse of 0, plus 2 to the 0 plus c. So tan inverse of 0 is 0. So this is 3, and you can check that on your calculator if you want. 2 to the 0 is 1 plus c, so c is equal to 2. So then my overall function would be y equals tan inverse of x plus 2 to the x plus 2. Okay, so basically this is more antiderivatives. They're just a little bit more complicated. You can always check them by doing the derivative. So get what you think the antiderivative is and then check, do you get back to the original thing? Solve the initial value problem explicitly, so that tells us we need to actually give like an explicit value for c. So first we need to figure out what the y function must have been. So y must be. So we've got 4 secant x tan x. So I'm going to look at my formula sheet. See how secant x tan x is here? Okay, that must have started as secant. So this would be 4 secant x. And then the integral of e to the x is e to the x. So that's this guy. So plus e to the x. That looks like an x. Let's make it a better plus. And then plus 6x. So again, think antiderivatives here. This must have been 6. X must have started as a 2. And then that 2 would have come down like that. So this would have been 4 secant x plus e to the x plus 3x squared. And that's what it would have gotten our 6x as our derivative. So then we have to figure out, okay, what is our actual c value? So we're going to plug in these values. So y equals 5 when x equals 0. So 5 equals 4 secant of 0 plus e to the 0 plus 3 0 squared. So for secant 0, you can do that on your calculator. Secant 0 is 1. So it's going to be 5 equals 4 times 1. E to the 0 is also 1. And then 0 squared, that term is 0. Oh, sorry, we needed to add a plus c. That's what we're actually solving for. That's our general thing. So then c is going to be equal to, so this side is 5, subtract that, so c in this case is actually 0. So then my original statement would be 4 secant x plus e to the x plus 3x squared. And that is my starting point, and my c is 0. The other way that we can do this is solve the initial value problem using the fundamental theorem of calculus. Okay, so if we think about what we used that for previously, we're just kind of going to do the opposite. So what this is saying is that the derivative of some function is this. Okay, now when we did the fundamental theorem, we were doing the derivative of the integral. So that's what we're going to plug back in here. So we're going to do the integral of this function. And remember how when we were doing fundamental theorem, there was always an x up here, and then we used a different variable. I'm going to use u because that's what the question is telling me to use. So 2 plus cos u would have gone in here, and then there would have been a du. So if we were doing the fundamental theorem, if we were doing the derivative of this integral, this x would go in, and it would give us this, okay? Now, how do we deal with this, okay? So if x is equal to 0, we have to think about how we can use that. If I take that x value and I put it down here, if I plug in an x is also equal to 0, then I'm doing the integral with no area. Okay, so then this whole thing would be equal to 0. This, remember, is my original function. So if u has to equal 3, if I plug a 0 in for x, or sorry, minus 3, it would have to be out here. Okay, so if I plugged a 0 in, I'd do the integral from 0 to 0. So this whole thing would cancel, even though normally if we were doing the derivative of it, we could just plug that x in. Because there's a 0 here and x is equal to 0, this whole thing cancels and u is equal to -3. So that's how we'd set that up. Okay, same sort of process here. So we've got h prime. Remember that is the derivative. So that means h, the original function, would be the integral. That's the ugliest integral sign ever. Of this. So let's use cube root of tan. Let's use t, because I feel like that's often something else we use. We could use u, we could use whatever, as long as it's not x. So the x is what would go in there. And we have to think, okay, what do we want this thing to start at? This tells us that h at 4 has to equal 5. So if I plugged a 4 in, it's going to equal 5. So if I use 4 there, if I plug a 4 in here, this whole thing's going to cancel, and then we have to add that plus 5, so that if I plug a 4 in, this whole thing cancels, and then h is equal to 5. Okay. The other part of this lesson is slope field. So we've done a little bit of this before. This is just going to be slightly different. So slope field sketches are used to show the family of solutions for differential equations. Remember that a differential equation just means that it contains a derivative. So if my dy dx is equal to 2, that means that my slope is equal to 2. Okay, so if I wanted to draw a function where my slope is equal to 2 at every single value, right, because this doesn't matter x, like if x and y change, my dy dx, my slope is consistent. So I could just draw those little ticks that we've drawn before as positive 2 slopes. So my function could look something like that, or something like that, or something like that, depending on what my c value is, right? My slope is 2 everywhere. If I have something a little bit more complicated that varies as x changes, it's going to look like this. So the slope, dy dx, m is equal to whatever x is plus 1. Okay, so this is a little bit trickier. So for this one, I like to actually give ourselves a little grid to work with. So if I plug in x is equal to 0, my slope is 1. So at all of these points, I'm going to just draw a slope that's 1 up, 1 over. If I plug a 1 in for x, then my slope is equal to 2. So anywhere here, my slope is going to be steeper. If I plug a 2 in for x, it's going to be even steeper still. If I plug a -1 in for x, then my slope is going to be 0. If I plug a -2 in, then my slope is going to be -1. If I plug a -3 in for x, my slope is going to be -2. So see how we can kind of piece together these bits and draw ourselves a function. Kind of looks like that. Okay, it could also be down here instead, because this is the slope. Those two functions are going to have consistent slopes at every x value. If dy dx is equal to sine x squared, this is slope is equal to sine squared x. I don't know why I wrote it like that, whatever. So then we're just plugging in x values again. So the other way that it makes sense to do this is give yourselves little points and then draw those little slope bits on your point. So give yourselves like a grid in points like that. And then say, okay, if I plug a 0 in for x, okay, sine of 0 is, remember that's here on my unit circle, sine of 0 is 0. Okay, so 0 squared is still 0. So this, the slope at all of the x equals 0 points is going to be 0. Sine of, I'm going to use this is pi over 2, and then this is pi. This is negative pi over 2. This is negative pi. Otherwise, it just is tricky. Okay, sine at pi over 2 is 1. Okay, 1 squared is a slope of 1. Sine at pi is 0 again. So 0 squared is 0. Sine at negative pi over 2, so it's down here, that's -1. Square it, you get +1. Sine at negative pi, that is 0. Square it, you still get 0. So my function might look something like that. Where my derivative, my slope, is sine squared x. If my slope field is x and y now is making my slope change, so m is equal to x times y. This one is probably the trickiest yet. So I'm going to start with my little dots because I just find it easier to draw a nice grid if I start with that. So like that. So then for every point, I'm going to have to plug in an x and a y. So if my slope is equal to x times y, at 0, 0, my slope is 0. At 0, so if my x coordinate is 0, so anywhere on this y-axis, those are all going to be 0 slopes. Same with if y is 0, so anywhere on the x-axis, these guys are all going to be 0 slopes. Okay? At x and y equal 1, my slope is 1. At x equals 1, y equals 2, 1 times 2 is 2. At x equals 2, y equals 1, that's a 2. And then if x and y are both equal to 2, that would be an even steeper slope. So that would be a slope of 4. Kind of exaggerating it. It looks straight up and down, but hopefully you get the point. Down here, if x is 1 and y is negative 1, 1 times negative 1 is a negative 1 slope. It's going to look like that. It's going to be a negative 2 slope, another negative 2 slope, and this is going to be a negative 4 slope, so even steeper. Down here we've got negative times negative, so negative 1 times negative 1, that turns into a positive 1 slope. Negative 1 times negative 2 turns into a positive 2 slope, positive 2 slope, positive 4 slope. This one, my x coordinates are negative, but my y's are positive, so negative 1 times positive 1 is negative 1, negative 2, negative 2, negative 4. So my original graph might look something like that. Or it might look something like that. Just depends on what my C value was. Okay. So those are slope fields. One last thing that we can do is we can match a slope field to its differential equation. So I'm going to actually look at them. So y prime meaning equaling 1 is my slope is 1 everywhere. So if we look at this one, see how every single one of those little points it gives us, my slope is 1. So the function that has a derivative of 1 would be this guy. The function that has a derivative of 0 would be my slope is 0 at every single point. So that would be b. That's d, my bad. My function that has my y prime, my slope being equal to x squared, we have to look at what that would mean. So if I plug a 0 in, I'd get a 0 slope. So now I'm looking for, we've done these ones. I'm looking for a slope at 0 at an x coordinate of 0. So this one has that, this one has that, nope. Yep. This one doesn't have a slope at x equal to 0, okay? If I plug a 1 in, my slope would be 1. 1 times 1 is 1. So this one would work, right? If I plug a negative 1 in, negative 1 times negative 1, this is also 1. So see how f meets the rules for every point there? So we've done that one. Y prime is equal to sine x, so m is equal to sine x. So if I plug a 0 in, this is going to have to be a 0. If I plug a 1 in, sine of 1, we're going to use pi's. We're going to pretend that these are like pi's. So we're going to do like pi over 2. Sine of pi over 2 is 1. And then sine of pi is 0 again. So it's going to fluctuate between 0, 1, 0, and then we'd have a negative 1. So we have at x equals 0, it should give us a 0. So this one, we have our slope is 0 at 0. And then if this first, so this one's tricky because it's hard to know what the divisions are, right? It's not divided as sine functions. But what we do see is that this, if we connect all of these, this would kind of look like a cos graph. See that? So we know that the derivative of a cos graph is a sine graph. So that's going to be this one's B. If we have y prime, so the slope is equal to -1 over x cubed, we're plugging in a 0. And so this is going to be one of those ones where there is no slope. So this one's either A or G. So see how there's no slope drawn at x equals 0 for either of those two? That's because if x equals 0, there is no slope. So now we just have to figure out between this one and this one, which of these are each of them. So if I plug a 1 in here, I'm going to get 1 cubed, which is 1, so -1 divided by 1, so -1. My slope is -1 at x equals 1. So because my slope is negative here in A, that means that this one has to be A. If I plugged a 1 in here, 1 divided by 1, this would give me the positive slope there. So this one is G, okay? Y prime equals cos x, so my slope is equal to cos x. Cos x at 0 is equal to 1, okay? So here, this one, we see kind of a sine graph forming as that derivative, and that's passing right through there. So this one's going to be E. And then this one is the only one left. So 1/2 x cubed. So if I plugged a 0 in, my slope would be 0, so that's here. If I plugged a 1 in, I'd have a slope of 1/2. If I plugged a 2 in, I'd have a slope of 2 cubed is 8, so 4. See how it's getting steeper and steeper and steeper, so this one's C. Okay. So for today, I want you guys to do, I wrote this at the top, but I don't know if you would have caught it. I want you guys to do page 331, numbers 1, 2, 3, 7, 11, 12, 13, 21, 22, and then 35 to 40. There's 2 parts in this, so this is a matching question. Just do the matching. You don't need to draw. So hopefully that will make sense once you read the question. Okay, so that's what you're doing for practice for this section. Okay, let me know if you have questions.